Hi there, welcome to this video. It's less than 2 weeks to go till Maths A level. How is revision going? Have you clicked on this video hoping to find some predicted questions that are actually going to be in the paper? Because no one can actually predict what will be on the paper. But looking at previous papers, the mock series from the exam board, you can get a good idea of the level of maths involved. And the exam will contain questions that will test your knowledge. Up to about 27% will be problem solving, and you should have by now seen some questions which are a little unusual. My previous video was on modelling, as pupils can find these hard, and in this video I have tried to find a mix where it's not obvious always what to do, and then also included some questions on topics I haven't already covered. As always, a like, a share at some point during the video whilst you're watching is greatly appreciated. Okay, let's get started. So you might turn over the page and see a question of the type you've not seen before. Do not panic. You know, there's plenty on there that you will have seen and it should be familiar, but there will be some that will test you. So try to reread the question, really understand what you're being asked, what topic area is. See if you can get a diagram to help you and annotate onto that. Just write down some formulae to try and puzzle your way through, but don't panic. There should be enough on the paper to get you a good grade. This is my first question. You can see I'm going to be summing some series, and in this first part I go from r equals 4 to infinity. You get the formula for an infinite series on the formula sheet for a geometric sequence, a over 1 minus r. Now what I can do is, even though to generate the first term that will be applied to this sum will be r is equal to 4, if I can just treat that as the a, it's just going to add all the terms up from that point onwards, so I can just treat that as the first term. So when r is equal to 4, then this first term will be 20 times 1 over 2 to the 4. 20 times 1/16 is 20 over 16, which is 5 over 4. When r is equal to 5, just to get an idea of how this sequence is going, it's going to be a half to the 5, which is 20 over 32, which is 5 over 8. Now, because I've got this half to the r, I am timesing by a half each time, so the sequence is going to go 5 quarters, 5/8, 5/16. My r, what I'm timesing by between each terms, is times by a half, and when I'm doing a series I'm just going to add them up. So putting the a and r into the formula, we're going to get the sum to infinity is going to be 5 quarters, the first term, over 1 minus a half, which is 5 quarters divided by a half, 5 quarters times 2 over 1, which is going to be 5 over 2. Now, if you wanted to put r equals 1 in and do the sum of the series all the way from 1 to infinity and then take away the first 3 terms, that would get you the same answer. So you could do it that way as well. Now in part 2, we're going from n equals 1 to 48 of this sequence here, but we've got a log sequence. So if we put n is equal to 1, I always try to put the numbers in just to get a feel for what's going on before I start to see the whole thing. So if n is equal to 1, you've got log to base 5 of 1 plus 2, which would be 3, over 1 plus 1, 2. So you can see when I'm going to be doing this fraction here, the one below is always going to be one below the numerator. So we're going to be summing up. So the next term will be when n is equal to 2. So this will be log to base 5 of 4 over 3 plus log to base 5 of 5 over 4 plus, and then if I look all the way up to the 48th term, it's going to be log to base 5 of 50 over 1 behind 49. Now what I can do is use my log laws, and every time I've got a division here, you're going to be writing a takeaway. So all the numerators are going to be adding. So if I start to put them, log to base 5 of 3 plus log to base 5 of 4 plus log to base 5 of 5 plus all the way up to the log to base 5 of 50. And then what you're going to be doing when you separate them by the log laws is taking away the ones that are underneath. So there'll be minus log to base 5 of 2 minus log to base 5 of 3, which will be this one. And then minus log to base 5 of 4, which will be this one, minus all the way up to log to base 5 of 49. Now what's going to happen, you've got a plus log to base 5 of 3 and then a minus 1 from it being in the denominator, and so on. You'll get all this crossing off. There'll be one behind the log to base 5 of 50 that's positive, and you'll be taking away that one. So the only ones that haven't got a match up is this one here on the top and this one here that's a minus 1 from being in the denominator. So that's log to base 5 of 50 take away log to base 5 of 2. And now you can use your log laws and put that 2 back underneath. It's log to base 5 of 50 over 2, which is log to base 5 of 25, which is 2, because when you do logs, the answer to the log is the power. 5 to the power 2 is 25. So there we have shown that it's equal to 2. This is another series question, and you need the formulae that S of n is equal to A into 1 minus r to the n over 1 minus r, and s to infinity is a over 1 minus r. That's telling us in this question that the sum to infinity is 8/7 the sum of the first 6 terms when n is 6. So that's a over 1 minus r is equal to 8/7 times a into 1 minus r to the 6 all over 1 minus r. Now what's the same on each side? We can cancel by an a, just dividing both sides by a. 1 minus r we can cancel, and then we can cross multiply this 8/7 and get that 7/8 is equal to 1 minus r to the 6. Rearrange, r to the 6 is 1 minus 7/8. So 1 minus 7/8 is 1/8, and then we'll have to take the 6th root. This is r is equal to 1/8 all to the 6th, and that will be plus or minus when we're taking an even root. So we can think of that as plus or minus 1 over 2 cubed all to the 1/6. 1 to any power on the top is going to be 1, but 3 times a 6, this is going to be plus or minus 1 over 2 to the half, which is root 2. So our k is equal to 2. In this question, we've got the graph with this function here. We've got max and min at P and Q. Part A says show that the x coordinate of P and Q are solutions to this equation here, which does look nothing like what the curve is, but we can see we've got a quotient. You get the quotient rule on the formula sheet, and in function notation, we need to differentiate to find max and min. I remember the quotient rule as bottom, which is e to the root 2x minus 1, differential of top. Now differential of sine is cos. The 4 is just going to join in. The 2 is going to come and multiply by the 4 by the chain rule, and that's going to give us 8 cos 2x. So it's bottom diff top minus top, which is 4 sine 2x, differential of bottom. E to the x differentiates and integrates to itself, but then we've got this root 2 here, that's just going to come down root 2 e to the root 2x minus 1 all over the bottom squared, which is e to the root 2x minus 1 all squared. Now when we have max and min, the differential is equal to 0, and if we cross multiply we can see that that's only going to equal 0 when the numerator equals 0, and so my next line will be to take out a factor of the e to the root 2 x minus 1 on the numerator, and that will be times by 8 cos 2x. This root 2 can come in times by the 4, so it'll be minus 4 root 2 sine 2x equal to 0. I've cross multiplied and got rid of that denominator, and now the f dash x is only going to equal 0 when that numerator equals 0. Now e to the root 2x minus 1, if you think about your exponential graphs, they go like this. The fact that we've got the root 2 and the minus 1, it's just going to move the graph to the right and stretch it, but it still won't come below the x-axis, so that's not going to give us a solution. It's only going to equal 0 when this thing in the bracket equals 0. So it's only going to happen when 8 cos 2x, we can take that term to the other side, is equal to 4 root 2 sine 2x. Now we've got an eye on where we're going, which is tan, so we want to leave the sine on the right and cross multiply, bring the cos 2x down, and bring that 4 root 2 down. So cross multiplying, the 8 is going to stay still, the 4 root 2 is going to come underneath, and then we'll have sine 2x over cos 2x, which is tan 2x. And then all we need to do is we can cancel there, and that will be 2. So we'll have a 2 over root 2, rationalizing the denominator. The root 2 by itself will cancel with the 2 there, so we'll just get that tan 2x does equal root 2. So we've done it for 4 marks. And part B, using your answer to part A, find the x-coordinate of the minimum turning points on the curve where we've got f of 2x here. Now our transformations of graphs tell us that when there's a 2 on the inside, that is going to halve all the x-coordinates. Now we're looking for Q because it's asking us for the minimum point. So that is a solution to what we found in A. So if we do tan to the minus 1 of root 2, and we have to remember that we're in radians, that will tell us what 2x is. And if you do that on your calculator, it comes out to be 0.955 or 4.0966. You get your 2 solutions. You just need to get your first one on your calculator and then add pi on, and then dividing by 2, x will be 0.4775 or 2.048. Now obviously the 0.4775 is the first one, so that's going to be where P is, 0.4775. Q is the 2.048 of the function, and then thinking about the transformation, this 2 here is just going to half that x-coordinate. So the answer for this one will be, the x-coordinate will be half of 2.048, which is 1.024. Now in part 2, we've got to think about our transformations of graphs again. We've got a 3 and a minus 2. Now they're going to both affect the y coordinates, but the fact that the minus here, the minus stretching the function, the minus on the outside is actually going to be a reflection in the x-axis. So it's asking us about the minimum, but when we reflect it, you're going to get the graph is going to come down here and go like that. So the actual minimum now will be the p-value, but the x-coordinate of the p-value won't change. It will stay here, which I've not drawn it quite symmetrically, is going to be there. The fact that we are going to be doubling it, timesing it by minus 1 and adding 3, those changes will affect the y-coordinate, but the x-coordinate will stay the same, but the minimum point will be at the 0.4775, so 4, 7, 8 to 3SF. Here's a parametric equations question, and for part A we're trying to get the Cartesian equation. Now when you've got the parametric equations usually given in sine and cos, you're looking to get what is worth a sine squared and a cos squared and put the equivalent together to make one. But here we can notice we've got a single t and a double, so we're going to be using our double angle formulae. If we rewrite the y equation to y is equal to 4 plus 2. Now we want to replace the cos 2t, but we want to involve sine to introduce the x variable. So the cos 2t has 3 different versions. I'm going to use the 1 minus 2 sine squared version, because then I can rearrange the x equation. X will be x minus 3 over 2, and then square it will be sine squared t, and then I can replace that in terms of x into my y equation. So y will be 4 plus, multiplying this 2 in, we're going to get 2 minus 4, and instead of sine squared t, I'm now going to put what I know it's worth from my x equation, which is x minus 3 all over 2 all squared. Now if I square that 2 on the bottom, that will make 4, which will cancel with that 4 there. These 2 here are going to make 6, so that's going to be 6 minus, and all I'm going to be left with here is the numerator, x minus 3 all squared. So we've done it. In part B, we're being asked to sketch the curve. So if we just look at the Cartesian equation, we can see we've got a quadratic. So let's start with that. Your basic x squared curve is like this, going through the origin. Then we've got the minus 3, so that's going to send it 3 to the right. And then the minus in front of the bracket is going to be a reflection in the x-axis. That's your smile frown, and then 6 up is going to mean it's going to come up like this. So that's the basic shape of the graph with this max here at 3, 6, and then we've got to have a look at the range of values, which are dictated by the range for t, because looking at the parametric equation, it's going to be dependent on the sign. Sign goes between 1 and minus 1. So what's the maximum value this can take? It's going to be 3 plus 2 and 3 minus 2. So the x values are only going to go between 1 and 5. So x is restricted between 1 and 5. Now notice, even though this has got to be less than 2 pi, because the max here occurs at pi by 2 or 90 degrees, which is in the range, then you can equal the 5. Okay, and then if we think about the y values, y is influenced by the cos 2t, so cos goes between 1 and minus 1, so we're going to have 4 plus 2, which is 6, so we are able to go to that max. So the graph is going to look like between 1 and 5, you're just going to get this part of the graph, and the max is going to be at 3, 6. We can have that. In part 2, we're asked to explain why it does not include the point. So why does it just stop and start there? It's because we're only having values that are for x between 1 and 5. In part C of this parametric equation question, we've got the line x plus y is equal to k. K is a constant, and this line has got to intersect C at 2 distinct points. State the range of k. So we need our graph again to have a think about this. It goes like this, between 1 and 5, and the max is at 3, 6. Now x plus y is equal to k. Is made up of coordinates where the two values together equal the k, but if we rearrange that, it's going to be y is equal to minus x plus k. It's going to have a minus 1 gradient. So we're looking for a line that's got a -1 gradient going through a k that crosses the curve at 2 distinct points. Now if I did one like this that's got a -1 gradient, that's only crossing at 1. So we can see the first line we're looking for is one that just goes through the end here. So we know that that point is where x is equal to 5, and we've got the line, or the curve, sorry, y is equal to 6 minus x minus 3 all squared. So when x is equal to 5, y is equal to 5 in there. 5 minus 3 is 2, 2 squared is 4, and 6 minus 4 is 2. So that's the coordinate 5, 2. So the line must be where x plus y is equal to k, and if x is 5 and y is 2, then the k is going to be 7. So that is going to be our first line where k has got to be 7, and then we can have lines that are higher up the graph, but then there'll be a point where we've got a line here where the graph is just tangent. The line is just tangent. And that is the point where the gradient of the curve is going to be -1. So if I write my curve as y is equal to 6 minus, and then squaring that bracket out, x squared minus 6x plus 9, which is 6 minus x squared plus 6x minus 9, which 6 minus 9 is minus 3 minus x squared plus 6x. And if I differentiate, so dy by dx is going to be minus 2x plus 6, and equate that to -1, then bring the -1 over. 7 is equal to 2x. X will have to be 7 over 2, or 3.5. So that is that point there, 3.5. And then if I find the y point, so put again 3.5 into my y equation, I'm going to have 6 minus 3.5 minus 3, which will be a half, and I need to square that. So 6 minus a half squared is a quarter. 6 minus a quarter is 5 3/4. So that will be my y point. So I'll have 3.5, 5 3/4. So this will be the line where x plus y is equal to k. 3.5 plus 5 3/4 is 37 over 4. So the range of k will have to be k such that 7 is less than or equal to k is less than my 37 over 4. And set notation like that. Now it's not equal to 37 over 4, because if it was equal to, it would only have the one distinct point, it would be tangent, and we want it to be lower than that. So that's why it needs to be not equal to on that second part of the inequality. Now another way to do this is to equate the two lines. So rearrange the x plus y equals k. You could have y is equal to k minus x, and then equate that to the curve 6 minus x minus 3 all squared. Take everything to one side and do b squared minus 4ac is equal to 0, which will mean we'll have a tangent, and solve for k that way. It will still come out to be the 37 over 4. This is a numerical methods question. We're going to be applying the Newton Raphson formula on this cubic. You get the Newton Raphson formula on the formula sheet. It is that the next approximation to the root is the previous one minus putting that previous one into the function, dividing by the differential of that previous one. So we just need to apply that to this cubic. Our next approximation is going to be our previous one minus putting x of n into the function here. It's telling us to do 2x of n cubed plus x of n squared minus 1 all over the differential of the function. So we just need to power down. That's going to be 6x of n squared, and then power down again. That's going to be plus 2x of n. Now all we need to do to get this single fraction is give this term here the common denominator. So that's x of n multiplied through by that denominator. Now I can take this minus into the bracket. So it'll be minus 2x of n cubed minus x of n squared and then plus 1 on the end all over the common denominator. And then just multiply this in. I'm going to get 6x of n cubed minus 2 here, which is going to give me the 4x of n cubed. I've got 2x of n squared minus 1, so that's going to be plus x of n squared. I've got the plus 1 on the end, and then the common denominator is going to give me my answer for part A. Now part B, it's asking us to put x1 equal to 1, get x2 and x3. So all we need to do is put x equals 1 into here to get our x2. Now this is telling us to do 4 times x1 cubed, which will be 4 times 1, plus 1 squared, which is 1, plus another 1, all over 6 plus 2. So that is going to be 6 over 8, which is 3/4. Now to get x3, just put 3/4 back into here, and if you do all that, it comes out to give you 2/3. So part C, explain why for this question the Newton Raphson method cannot be used with x1 is equal to 0. Now just to explain what's going on with the Newton Raphson formula, when you've got some curve and you're approximating for the root, say we thought the root was here, you draw a tangent to the curve, and what you are doing is finding here, this is f of x1 because this is our approximation here. This is our next approximation because we use the tangent and the gradient of that tangent is constant, and that is f dash of x1. So all you do is find an equation for that gradient, which is just rise over run. So that is f of x1 divided by, what's this distance here? It is x1 minus x2. Now if we just cross multiply and get that x1 minus x2 is equal to f of x1, which was our y height there, over now the gradient at x1. And then if we just rearrange for that x2, because that's our second approximation for the root, and then you'd be finding a tangent and trying to home in on that root. So if we just cross them over, x2 is equal to x1 minus f of x1 over f dash of x1. So it relies on the fact that this tangent is going to come down and go through the x-axis. Now when we put x1 equals 0 in, we can see that f dash of 0 is going to be 6 times 0 plus 2 times 0. So that's going to be 0. So at x equals 0, there is a stationary point. Because if the gradient is 0, then that tangent is going to be horizontal, and it's not going to find us our next approximation of the root. So that is why the Newton Raphson cannot be used, because the tangent to the curve at x equals 0 will be horizontal, because at 0 we have a stationary point. In this next question, we can see we're going to be integrating tan to the 4, and it's given us a helping hand in part A by asking us to put tan to the 4 in this form, and I can see I need some sec squareds and tan squared, so we're going to be using the identity that tan squared x plus 1 is equal to sec squared x. So if I rearrange that, tan squared x is equal to sec squared minus 1. So let's try and use that then. Tan to the 4 of x is equal to, now I want to have some sec squareds and tan squareds, so I'm going to write it as tan squared x and use one of the tan squareds to write as sec squared x minus 1, but then leave the other one there because I need a mix of both. Now multiply this in, it's going to give me my sec squared x tan squared x minus a tan squared x. And now again I need to use the substitution for tan squared, which is our sec squared minus 1. So that's sec squared x tan squared x minus sec squared x minus 1. Take that minus in and we're going to have it sec squared x tan squared x. It's going to be plus 1 minus sec squared x. So that is part A. Now part B, we need to integrate tan to the 4x. And we're going to integrate what we've just found tan to the 4 of x to be sec squared x tan squared x plus 1 minus sec squared x dx. Now tan x differentiates to sec squared, so sec squared on the end there is going to integrate to tan. The 1 is easy to integrate, we just need to worry about this term here. Now because the differential of tan is sec squared, we can think about the chain rule. The inside function here is tan, the differential is just sitting there, so if we just think about the inside function and integrate with respect to the squared there, we're going to get that this is 1/3 tan cubed x, because if you think about differentiating that, if I write it out again, if we power down, that will cancel with the 3, we'll be taking 1 off, so you'll go 3/3 tan squared x multiplying by the differential of the inside, which is sec squared x, so they'll cancel. So we're going to do that first term by reverse chain rule, then we're going to add on the integral of 1, which is just x, and then minus the integral of sec squared, which is just tan x, and we're going between 0 and pi by 4. So putting those limits in, you're going to get pi by 4, which is 45, tan of 45 is 1. So 1/3 times 1 plus pi by 4 minus tan of 45, which is minus 1. Minus, now when we put 0 in, tan of 0 is 0, plus the 0 for the x is 0, and then 0 again, so the second limit going in is 0. So all we're going to get is pi by 4 plus 1/3 minus 1 will give us minus 2/3. In this next question, I can see I'm going to be differentiating and I've got a product and I've not got the equation given explicitly in terms of y, so I'm going to be using implicit differentiation as well. So the product rule says that it's first, differential of second, differential of tan is sec squared y, but because it wasn't x, we must multiply by dy by dx. So that's first differential of second plus second, which is tan y differential of first, which is 2x tan y, is equal to differential of 9 is 0. Now I can see where I'm trying to get to doesn't contain any y, so I need to think, how am I going to substitute for sec squared y and tan y? I'm going to use the identity that tan squared y plus 1 is equal to sec squared y. And then from the question I can see that tan y is equal to cross multiplying 9 over x squared. So tan squared y is equal to squaring that fraction 81 over x to the 4. So substituting these back into my product rule, I've got x squared. Sec squared is tan squared y plus 1, so that'll be 81 over x to the 4 plus 1. dy by dx plus 2x times tan y, which is 9 over x squared. Now instead of writing 1 in that bracket, I can just write that that is x to the 4 over x to the 4. And then if I put equal to 0, I can take that term over to the other side. So writing x squared 81 plus x to the 4 all over x to the 4, dy by dx equals minus, and then the 2 and the 9 can times together and give me 18x over x squared. Now I'm not going to cancel that x squared there because this x squared and the x to the 4 will give me an x squared there, and then I can just times both sides by the x squareds, which will get rid of those, and then all I've got on this side that's being multiplied by the dy by dx is the 81 plus x to the 4. They've got it the other way around, but I can just cross multiply and get that dy by dx is equal to minus 18x over the x to the 4 plus 81. So that's part A. Part B, prove that we've got a point of inflection at the 4th root of 27. So just to explain a little bit about points of inflections, say I had a cubic that would have a max and a min. And if I differentiated where the cubic has its max and its min, when we set the derivative equal to 0, that finds us the roots. So where that one has its max would be where this one would have its roots. And then if we differentiated again, where this one has its min would be here, and we would go to a straight line. So if this is cubic, this is quadratic, and then this is just linear. So the points of inflection are where the original curve, the gradient of it, stops from slowing down to speeding up. So you can think here as we go up to our max for our cubic, the gradient is positive, but it is slowing down to 0, and then it continues to slow down because it's negative. So that's coming down here. And at this point here where the first derivative has its min, the gradient starts to speed up. So that will be the point of inflection. It's where you go from being concave, the gradient slowing down, to being convex, the gradient speeding up. So at that point there is where this one stops slowing down and starts increasing again, which is this point here. So the second derivative at a point of inflection is 0, and either side of that point of inflection, the second derivative is going from negative to positive or vice versa, but you're looking for a change of sign. So what we need to do is find the second derivative. So d2y over dx squared is going to be bottom, which is x to the 4 plus 81, differential of top, which is minus 18, minus top, which is minus 18x, differential of bottom, which is just 4x cubed, and that space there, all over the bottom squared, which is x to the 4 plus 81 all squared. Now when you put the 4th root of 27 into that numerator, you're going to get 0, and we're going to expect to have the second derivative equal to 0 at the point of inflection. Now when you do the 4th root of 27, it comes out to be 2 point something. So if we look at either side and we find what the second derivative is at maybe 2 and 3, so at x equals 2, if you put 2 into this numerator, you can see that the denominator is going to be positive, so all you need to do is put it into the numerator. But at x equals 2, the second derivative is less than 0, it's negative, and at x equals 3, so going the other side of the point of inflection, the second derivative is positive, so we have a change of sign. And also at the 4th root of 27, the second derivative is equal to 0. So that's telling us we've got a point of inflection. Thank you so much for watching. I hope that these questions have helped with your revision. Please do give it a like and subscribe. That's greatly appreciated. Keep an eye out on the channel because I'll put some more videos on the run up to the exams and during the exams, and I'll probably do some analysis as the exams happen as well. Okay, good luck in all your exams this summer, and I will see you on the next one.